Hi everyone. So I wanted to go ahead and make a video where we discuss some of these solutions from the first exam more in depth. So, without further ado, I will switch over and we can just start taking a look at it. Okay, so I just have a copy of the exam pulled up on the screen here, and we will just go through the problems one by one. Okay, so in this first part, the name of the game is we want to solve these equations for x, which means we'll need to put our algebra skills to good use. What's going to complicate things a little bit is that we have these unknown numbers floating around, denoted by capital Greek letters. So there we have a capital lambda, capital gamma, and capital sigma. Again, just remember this notation means these are real numbers, so they're not unknowns, they're not variables like x and y. They really are just some specific number. We happen to not know them. So we have to kind of carry them throughout the problem as we go. Again, if you want, in your Scratch work or something to plug in something like, lambda equals 3 and do the entire problem and carry around this 3 without simplifying it, without adding it or multiplying it or dividing it, and combining it with other numbers in some way, you can do that. But I would try to practice this skill of just leaving it as an abstract symbol and just carrying that throughout the problem. So let's go ahead and look at this first one. So we have this equation 1 divided by root x plus 3 is equal to lambda, and we want to free that x from under there. Okay, so the first thing to do here is I would think about trying to clear denominators is always a good idea. Usually a good idea. In this case, I think it'll work. So what I want to do is maybe first I'll just rewrite the equation as I see it. 1 over 8x plus 3 is equal to lambda. And I don't want to modify this in place, so I think what I will do is just make a copy of this. If I were in my Scratch work, I would just rewrite it down here. And I would now think about multiplying this in this root 8x plus 3, this entire quantity multiplied in on the left-hand side, as well as multiplying in that entire quantity on the right-hand side. So I just need to be very careful that I'm applying this multiplication operation to the entirety of both sides. And why did I pull this maneuver? Well, because on the left-hand side, we're kind of seeing some cancellation. I sort of cooked it up so that this and this, when I divide them, I'll just get a 1 out of it. So that was the whole point there. So the left-hand side, so I should say that the first step logically implies this second step, which logically implies this third step, where now what do I have on the left-hand side? Well, I kind of orchestrated it so that I would see a 1 there. I really wanted the left-hand side to be simpler. Now I just need to see, okay, I did this at the cost of making the right-hand side more complicated. So let's just see what we're left with. I think really there's not so much we can do. Maybe I'll just change the order of them here. Maybe there's not much we can do at this step to simplify it, much more than that. But now maybe what I want to do is take this entire equation, let's make a copy of it up here. So this will be our next logical step. And what is that step? Well, I'm going to apply an operation again to both sides. I'm going to apply it to the entirety of both sides, where I square them. Okay, well, it seems that leaves the left-hand side fortunately pretty simple. And now we just need to be a little bit careful, because as we're squaring it, we need to make sure that we distribute this exponent to both terms. Okay, so I see something that looks like this capital lambda squared, multiplied by something, so I'll write it in kind of a funny way at first. Root x plus 3, that quantity squared. But really, why did I square both sides? It's really because I wanted to sort of cancel this operation of the square root happening, and I kind of squared it in order to cook up this cancellation. So I'm seeing something that actually looks like just this. Right? And I should be careful here, right? Because I just did an operation that's supposed to set off some warning bells. Should be some alarms going off. I've squared sort of this square and square root pair. We know that there's, sometimes this goes wrong. In this case, so let me zoom in here. there was one we had to worry about where it's you take something, you take the square root of it, so maybe I'll just write this as question mark, and you square it, and that equals something. And then there's this thing where we do it in the other order. We square it first, and then we take the square root of that entire thing. And one of these we had to worry about, one of these we really didn't. The one we don't have to worry about is this one. Why is that? Because the thing we might have to worry about is, does it change the sign? Does it send my positive input to a positive input, but then also send negative inputs to positive inputs? And so I guess maybe another way to see it is that the second one is the one we have to worry about, because this equals the absolute value of question mark, whatever I sent in there. Right, because if I take a negative, if I take a positive and send it through, then the square and the square root just undo each other. I get a positive number coming out, everything's fine. If I send in a negative number, then I square that as the first step. It turns that negative number positive, and now I'm taking the square root, I'm getting some positive number out. So it looks like my original question mark, but now the sign is flipped from a negative to a positive. And that's just a lot of words to say that I've recovered the absolute value of the input. Okay, so this is the one I have to worry about. How do I know that this is the one I don't have to worry about? Well, I mean, if you want, it really is the absolute value as well. But the thing is that we couldn't even send in a negative question mark in the first place, right? For this one, the first operation we're hitting question mark with is taking a square root, and we know that negative numbers aren't even in the domain of square root. So this is like the square root were a computer program or something. It would throw an error if you try to send in a negative at all. Okay, so which case are we in? We're in the case where we took the square root first and then we squared, so we're in the case where we don't have to worry about it. But it's really important to have this alarm bell go off anytime you're doing this canceling pair of square and square root. Okay, so back to the main sort of line of thought here. We want to now, the goal here was we want to free that x. So I think what I'll do in this next step, again, maybe I won't modify this in place, I'll just make a copy of it. I think what I would like to do is get rid of this lambda squared that I see, and I need to do something to both sides in order to make that happen. So I'm just making a little bit more room here. And I think the operation that'll undo seeing that lambda squared on the right-hand side is multiplying in by a 1 over lambda squared on both sides. And I need to be a little bit careful because I need to apply that to the entirety of each side. And okay, the whole point of this maneuver was that this thing and this thing, when I multiply them together, I get 1. So I kind of cooked up this cancellation. So what do I end up with on, say, the right-hand side? Well, I just have that 8x plus 3 left. What do I have on the left-hand side? I have something that looks like 1 over lambda squared. Okay, and so that's the next logical step. And I guess now that I just see parentheses on the right-hand side, I can go ahead and remove those because I don't have to worry about things being grouped up together anymore, at least not too much. And now what do I want to do? Maybe I'll just do 2 steps in one now because we're finally at the stage where we're just doing kind of arithmetic operations. We're just doing, so let's see, what do I want to do? I want to subtract 3 from both sides. So the way I'm thinking about that is I can move this over here as long as I put a negative sign on it. There we go. Okay, and I guess it's important to remember that this is like its entire quantity. I don't want to accidentally combine that fraction in the wrong way. And now I want to move that 8 to the other side. So I can do that by multiplying through by 1/8. I just have to be a little bit careful to multiply it to the entire left-hand side. And honestly, I think you could simplify this if you want. Like maybe you could try to put these over a like denominator and you could multiply in the 1/8. But this is really, I think, where I would stop. This is a perfectly fine answer. Right, so we have x equals some stuff, and the stuff that I'm seeing on the other side doesn't involve x. So that's, I'd say that's a good answer. Okay, so let's take a look at this. Let me kind of move this stuff out of the way a little bit. All right, so I guess the one thing we should always remember to do is, box our answer, highlight it in some way. Remember that the original question was asking us to solve for x, and we have now solved for x, so we should tell the reader that that's the answer they should go looking for. Okay, so now I have another equation here, this 3x minus lambda, and I'm taking that quantity and squaring it, and it's equal to 7. Okay, so I'm just going to rewrite the equation first. 3x, or sorry, I said lambda, this is actually a gamma. Very easy to confuse these two. So 3x minus gamma, that quantity squared, is equal to 7. And it might be tempting, I think, here to multiply this out, and let's see, what would you get? Something like 9x squared minus, I don't know, 6 gamma x or something, plus gamma squared equals 7. And then, okay, maybe you could subtract the 7 over and hit it with the quadratic formula, but then, you know, oh geez, what's the equation that I need to remember for the quadratic formula? So it maybe makes things a little bit more complicated than they need to be in this case. We're actually in kind of like the best situation we'd like to see. We're kind of one operation. So on this side, I'm just seeing the entire left-hand side being squared. So I have kind of one operation being applied to one side. I know I can just undo that operation. Well, in this case I can, right? Because square, I have this square root operation that undoes it. So in that case, what I'd like to do, so this is kind of my starting point. I've just rewritten the equation. I want to perform some operation on this entire thing. The operation I will perform is taking the square root of both sides. So I just need to be a little bit careful and make sure I do it to the entirety of both sides. Okay, what does that maneuver buy me? Well, maybe I hope to see something like 3x minus gamma on the left-hand side, and okay, square root of 7 on the right-hand side. But this should be, again, one of these steps where and there should be fireworks going off, alarm bells. I've done a square and a square root together, and I know that one of these cases has some little something I have to worry about, and the other case doesn't. But anytime I see these two pairs together, I should be thinking about, do I need to go check to see if there's an absolute value or a plus or minus or something? And in this case, this happens to be the one we have to worry about, right? Because if this thing was negative and I squared it, then I made it positive, and I took the square root, I got some positive number out of it. So I've sent my negative number to a positive number, and so what I'm getting is the absolute value of this thing. Okay, and then we saw this trick in class. There's a way to get rid of the absolute value. So I'll just copy this up here. I should maybe tell my reader that this is the flow of logic. This is the next step. So I can get rid of these absolute values, provided so maybe I'll just leave this grouped up on the left-hand side, provided I hit the other side with a plus or minus, but I have to do it to the entire right-hand side. Okay, so just rewriting this, I'm not going to do anything in this next step. So 3x minus gamma is equal to plus or minus root 7. Okay, and now I'm pretty much home free. I'm back to the, just doing arithmetic operations, so multiplying, dividing, subtracting, adding, that kind of stuff. Maybe I'll skip over, well, okay, let's just do this, and I'll show you. So you could just jump directly to the answer now here, since there's only sort of 2 steps left if you want. But just to show you kind of what's happening here, I want to move this gamma to the other side. So I need to add it. Okay, and that's equal. And I want to now move this 3 to the other side, but then I need to change it to a 1/3 and multiply the entire right-hand side. So you can do that in a couple of separate steps if you'd like. But at this point, we've just done sort of arithmetic operations, so you don't have to tell the reader about that necessarily if you don't want to. And now I have something I see where it's x on the left-hand side in terms of a bunch of stuff that, okay, it involves this unknown capital lambda, but it doesn't involve x, which means I am good to go. That is the answer I wanted, so I will box it, I will highlight it, I will put a period on it or something, to indicate to my reader that that is the solution to the question they asked, which was to solve for x. Okay, so let's look at this next one. We have something a little bit tricky, so I'll just go ahead and rewrite it. We have x, let's see, there we go. x over x plus, this is a capital sigma, is equal to 3 over x. Okay, so I think it's really tempting here. The first thing you might want to do is try to like cancel through the, like somehow through the fraction. But this is something, it's a little bit mathematically illegal. Somehow we need to think about this whole thing in the denominator is it's all sort of grouped together, and unless we have a way of convincing our reader we can split it apart into a couple of different fractions, then that kind of thing won't work. So what I will do here, so the first one was just rewriting the equation, now I want to do some kind of operation on it. So the operation I'll do, and let me see if we make some room here, is I will multiply in on both sides the thing I see in the denominator on the left-hand side. So I'm going to multiply that in, but I need to just be careful because I have to multiply it to the entirety of the left-hand side and the entirety of the right-hand side. Okay, so what was the point of this maneuver? Well, the point was that I really wanted to see this thing cancel that thing. So I get something that looks like, well, just the numerator left over on the left-hand side. On the right-hand side, I just have to sort of pay the consequences of my actions here, where I multiplied through and just see kind of what I get out of it. So maybe this is going to be a fraction of some sort. I see a 3, and I see an x plus capital sigma, and I see an x in the denominator. And maybe what I'll do at this point is I'll go ahead and distribute this 3 in this step, just to combine a couple of things. So I get something that looks like 3x plus 3 capital sigma. Okay, again, I'm just on a mission of clearing denominators here. That's kind of a general guideline that tends to work with these sorts of problems. If you can clear the denominators, things get a little bit easier. So here I've just rewritten the equation. I now want to do some different operation on it to clear that denominator on the right-hand side. So what I'll do is maybe I'll come in and multiply on the left by an x, or sorry, on the right. Okay, so I'll just multiply the entirety of both sides on the right by this quantity x. The whole point of this maneuver being that I want these two guys to cancel out. So on the right-hand side, I'm seeing, well, it's just the numerator left over, 3x plus 3 capital sigma. On the left-hand side, just paying the consequences, I have an x squared. Okay, so now, I mean, yeah, it's a little bit difficult. There's sort of a, if you've seen it before, you kind of know what to do, but if you haven't seen it, it's easy to get stuck here. But a general word of advice is if you've cleared denominators and now you have some stuff involving x all over the place, a good step is to always just collect terms. Put everything on one side and set it equal to 0. The reason to do this is because we have a lot of stuff from previous classes for solving when our equation's equal to 0. Right? So these are like finding the roots of a function. And here I'm seeing something that looks like an x squared, so I'm thinking that if I collect all of the terms, this is going to look like a quadratic, maybe, because I'm seeing a power of 2, and it's just like a polynomial in this x. And by that I mean there's no exponentials, there's no logs, there's no sine or cosine or anything. So I think in this case, maybe the quadratic formula is going to end up helping me. Okay, so what do? Is I just collect up all the terms on one side. So here I'm just moving everything from the right-hand side over to the left. And I just need to be careful with my signs. They come in with a negative sign once I move them over. And I see something that is set equal to 0. And then you might try to look at this and say, okay, maybe I could try to factor it. Maybe I could try to get this as like something that looks like x plus question mark squared equals 0. That would be pretty nice. Or if it was x plus question mark plus, or multiplied by x plus some star equals 0, that would be pretty nice too, because then I could just read off what the roots are. But in this case, I don't see an easy way to do that. So we can just think of this as, we can do quadratic formula on this guy. So we have like an a is equal to 1, just the coefficient in front of the x squared. We have a b, whatever is in front of the x. I'm seeing a negative 3. And a c, okay, I have to be a little bit careful because it's whatever the constant coefficient is, and I'm seeing a negative 3 with that capital sigma coming in. So But again, we have to remember that sigma is just some number. It's not an unknown, it's just a number that's unknown to us, but it actually is a number. Okay, and then I just have to remember what does the quadratic formula look like? Well, it says that if I have this quadratic set equal to 0, then the roots of this quadratic are, okay, let's see, x is equal to negative b plus or minus, let's see, root 4ac, or sorry, b squared minus 4ac, and we need to take this whole thing and divide it by 2a. But okay, good, I have names for everything that's appearing in that equation. So, okay, negative b, so we have x is equal to, so negative 3, so I'm seeing a positive 3. And there's a plus or minus. I'm going to put some stuff under a square root. So I want to see a b squared, so that's a negative 3 squared, which is a 9, minus a 4 times an a times a c, so that's 4 times 1 times whatever c is, so c was negative 3 sigma. Okay, maybe I'm just using a slightly different notation here. I'm just going to say we're raising that to the 1/2 power to avoid having to draw the square root in a weird way. Remember that these are the same thing. And then I need to divide this entire thing by 2a, but a was just 1, so I see a 2 there. And gosh, maybe I could simplify this a tiny bit, but I think that's pretty much as simple as it gets. So I see a 3 plus or minus. So maybe I'll just see that there's a negative 4 and a negative 3 happening there. So I'm seeing a 9 plus 12 capital sigma. I raise this entire thing to the 1/2. I put this all over 2, and I think that is about all we can do here. You may, if you want, distribute that fraction in. So this is 3/2 plus or minus 1/2 the root of that thing, but any of these are all totally equivalent, and I think that's about as much as we can simplify it. So I have x. Like how do I know that I'm done? Why have I boxed things? Because I have x on the left-hand side in terms of a bunch of stuff that doesn't involve x. So that's when I know I can put a box around it, highlight it, put a period on it. That is the solution to the question the reader originally asked. I will note really quick that this was kind of a roundabout way. One thing you can do here that is sort of a shortcut for this process is just cross-multiply these guys. So you would get something like x squared is equal to 3 times quantity x plus sigma here, and that results in exactly the same solution. It just skips a couple of steps. But if you haven't seen that, this process of just clear denominators and collect things on one side tends to be a pretty good way to go. Okay, so for this next question, okay, so we are given, let's see here, we're given the graph of some function, h of x. It looks like this function is probably a piecewise defined function. We're seeing that it's not, for example, defined in this region around 0. There's no part of the graph above it. It's just defined over here, and then there's a little piece over here. And we are supposed to use this graph to answer some questions about it. Okay, so the first question is, we want to know what is the domain and what is the range. Okay, so we've seen in pre-classes there are a lot of ways to think about this, but the domain is is what is the set of valid inputs to this function. What x values does the function know how to evaluate? And one way to think about that is that if you take the graph, we're really just looking at what copy of the real axis, the real line on the x-axis is underneath the graph. So what's the shadow if you put a light above this graph and cast it down? So what I would see here, right, if I put a light up here, for example, what part of the real line am I seeing down there? I'm seeing kind of corresponding to this open circle. I'm seeing something like that. So I need to leave out this endpoint here. And corresponding to this open circle, I'm seeing one of these guys. So I need to leave out that endpoint too. And so I guess I should go ahead and include that. So that is let me go ahead and tell my reader what I am computing. This is the domain of h, and it's going to be a couple of intervals. So this first interval, I guess this starts at -3 and goes to -1, but I leave out the endpoints. Okay, so that's just coming from the purple thing. And I'm going to write this funny u for this union symbol to tell the reader that there are some more intervals that I have to add into the domain. Now I'm thinking about over here, looking down from above the graph, what parts of the x-axis do I see below it? So same deal, under this open dotted line, I see something like that, so I need to leave out that endpoint. And under this closed dot, this is saying I can include that. Okay, so I guess in that first case, it was like all of this stuff here was in the domain because I can find points on the graph anywhere above that. And here I'm saying all of this stuff, let me do the same color here, all of this stuff is also in the domain because I can look above it, find a point on the graph, so I know how to evaluate this function. If I want to evaluate it at 1.5 or something, I just go up to the graph, and that gives me a y value. In this case, the y value is 2. So all of that stuff is in the domain, so I just need to tell the reader about it. So I need to leave out, positive 1, but include everything up, almost all the way up to 1, but I just need to leave out 1. And then I can go all the way up to 2, and then I can include that endpoint 2. Okay, and I just need to double check, are there any points in the domain I've left out? Well, no, I don't think so. There were just these 2 pieces of the graph, and I've looked at all of the x values below the pieces of that graph, and the graph doesn't exist anywhere else. So for example, like 0 is not in the domain, because if I look above that, I don't see any piece of the graph telling me what the output of that function should be. So this function does not know how to evaluate 0, for example. Okay, so I think we have the domain pinned down, so I'll kind of get rid of all of this so we don't clutter it up too much. Now let's talk about the range of h. Okay, and the idea is I can play the exact same game where I just want to shine a light on things and just see what values of now the y-axis I'm hitting. That's sort of the mnemonic device. The actual thing that's going on here is what the range is the attainable values, the y values, the output values of this function. So what's happening here, if I kind of focus on this second piece on this first piece on the left, I kind of look over at what I'm seeing on the y-axis, I'm seeing, well, so this point is actually on the graph, there it is, so I can include this point here, that's an attainable output value for this function. And let's see, maybe going up here, I'm seeing some open dots, so nothing but open dots. So when I trace this over here, I'm kind of seeing an open endpoint to the interval there. You just have to be a little bit careful because even though this one was open, that doesn't necessarily mean that this is always an open interval. For example, if this one was a closed dot, that's telling you that this endpoint you would now have to include because 3 is an attainable output. There's a point in the function that attains that output. But here they're both open, so we can leave this open. And then I should also double check, look off to the right hand side. Do I see any parts of the graph that achieve the value y equals 3? And I'm seeing nothing over there and nothing over there. So I know for sure I need to leave that out. But then I'm seeing everything in here is an attainable output. For example, there's, or if I fix this point here, 2.25 or something, I can trace it over and find some point on the graph that achieves that output. Okay, so just now telling the reader about what I've discovered here. This is saying that what range needs to happen here. Let's see, so I started at 1, and I can include that. And I go all the way up to 3, and I do not include that. Right, because that's corresponding to this open interval at the top here. And now the question might be, do I need to union in some more stuff? Because we only looked at one part of the graph, and there's this whole separate piece of the graph on this side. And in general, you do. But here we see that all of the achievable y values that are happening here, we've kind of already accounted for them, right? Because the only y value, this is all along the line y equals 2. And if I just go look at y equals 2 on the y-axis, I see, okay, we've already accounted for that because this part of the graph is also achieving y equals 2. So you might need to like union in just this 1 point set 2, right? Because that's all of the y values that are achieved by this part. It's just the constant function that's always taking on the value 2. But we really don't have to include this, right? Because there's a 2, but 2 is actually already in there. So we've already told the reader about it. Okay, so I have my final answer, my domain and my range. I'll box it, highlight it with a permanent highlighter, put a period on it or something, whatever I can use to indicate that that's the answer I want them to read. All right, this next part of the question asks us, we want to determine the intervals where the function is increasing, so that's the keyword here, increasing, and the intervals where the function is decreasing. So again, we'll just go back to the picture. So we have to sort of use the graph to reason about everything here, so we don't have an equation for this formula. And just intuitively, I mean, you should look at this graph and, all right, so increasing is kind of like you're going uphill, right, and decreasing is kind of like you're going downhill. So if you look at this part of the graph, we're not increasing or decreasing, we're staying at the same y value. Over here, though, we see that there's a little bit of both. There's some increasing and some decreasing. So maybe I'll just tell you the answer straight away is that if I kind of fix this point here and just think about all this stuff, this is sort of a downhill part of the graph, so I'm seeing some decreasing there, decreasing for that part. If I look at the right-hand side, I'm seeing some increasing as it goes up. How would I actually determine this precisely? I mean, so if you just saw this and you write it down, that'd be totally fine. If you're kind of confused about why this would be increasing or decreasing, there is a way to check this. So what you can do is you can just think about putting a line here. So there we go. Let's just think about this point. I want to know, is the function increasing or decreasing at this point? What I can do is think about a tiny little tangent line at this point, kind of just running through that point, and just tangent to the graph there. And I can just ask myself, is the slope of this tangent line positive or negative? And then a positive slope is like going uphill, and that's increasing, and a negative slope is decreasing. So here I'm seeing a line that kind of looks like this right there, and that's something with a negative slope. So for example, I know it's decreasing at this purple point. And I could think about sort of all of these other points, like is it decreasing here? The same argument's going to work. I just draw a tangent line. I see its slope is negative. Is it decreasing here? I see it's negative. Is it decreasing here? Well, okay, I draw a tangent line, and it's horizontal. So the slope is, I guess, 0, right? So it's not increasing or decreasing at that point. But if I go over here now and think about this point, I draw a little tangent line, and I see I'm getting a line now with a positive slope, so this is a place where it's increasing. And the same thing will go for any of these points on this sort of little piece of the graph here. Okay, so let's summarize what we have here. We had decreasing for everything here, and we don't include this point. It was just constant there, so that's all the increase or decreasing stuff. And on the other side, not including that point, we had all of this stuff over here, which was increasing. And we have to leave out the endpoints, of course. And then over here, we don't have to worry about, it's just a constant function. It's not increasing or decreasing. Okay, so now I just need to convert that into some intervals. So I just kind of look at what is the part of the x-axis lying underneath these. So I'm seeing -3 that I don't include. So I guess here in pink, -3 to -2, where I don't include -2 because it's just that you have that horizontal tangent line there, so it's not increasing or decreasing. And where is it increasing? Well, essentially -2 to -1. Okay, so I just need to tell the reader about this. So increasing somewhere, and it's decreasing somewhere else. And where is it increasing? Well, it was -3 to -2 was the interval. And where was it decreasing? If I just go back up to the picture, that was this one here, which was -2 to -1. And that's exactly what they asked, and I provided an answer, so I'll box it and highlight it, and just double check, have we actually answered the question? Yes, they asked about where it was increasing and decreasing, and we provided some intervals that say that. Okay, so let's talk now about this question here, which is write a formula for h as a piecewise function. Okay, so, and they're giving us a hint here that the curved part on the left, that piece of the graph was a parabola. So what is happening here is, let's kind of erase this so you don't clutter it up too much. So I want a formula for this left-hand part and a formula for this right-hand part. So I think maybe the easy one, right? So maybe I want to call this like an h1 of x, will be one of the pieces. Maybe an h2 of x will be another one of the pieces. But I think I can write this one down right away. All right, so this is the function that no matter what x value you give me, I just give you the output value y equals 2. It's just h of x equals 2. And we could just imagine this being defined everywhere, right? And this would just be a line. Here's the line, h of x equals 2. But now we want to tell the reader to, okay, don't do that function everywhere, only do it in some little restricted region. So maybe for x in some interval. And what interval was that? Well, it's the same one we had before. It was 1 to 2. Okay, so maybe that one's not too bad. And we'll come back to defining this as a piecewise function. We need to figure out a formula for this guy. And we've been, we got a hint that it was a parabola. So I'm thinking there's probably a parent function, f of x equals x squared. Maybe do it in a slightly different color. Equals x squared. So I kind of know how this function goes. Actually, I should start with a couple of the important points. I know it goes through 0, 0, 1, 1, and negative 1, 1. And it kind of arcs through those, something like that. And now I kind of want to do something to move that up to that one. Okay, so it looks to me, let's trace where the vertex goes. So here's the vertex. There's the vertex. So I'm seeing that I need to move the vertex over by 2 to the left, and I need to move it up by 1. So I'm suspecting that what's going to happen here is I need to have h1 of x. So maybe it's going to be x squared, but I need to maybe add some modifications for it. Let's see, to move it 2 to the left, I need to add 2. Remembering that changes to the input, changes horizontally, have this counterintuitive behavior. You might think that you would subtract 2 to move it to the left, but you have to kind of do the opposite thing. Okay, and how do I move it up by 1 unit? Now I can modify the outputs of the function by doing that. So this is now outside the x squared evaluation. And now I just need to be a little bit careful because this one I'm seeing up here is like a little bit stretched. I'm seeing that, well, okay, maybe an easier way to see it is if you look on the original graph, there's kind of this 1, 1, slope 1. Well, that's the easiest way to say it. If I start at this special point 0, 0 and I go over 1 and up 1, I get another special point. But here I'm seeing that that doesn't really happen. If I go over 1 and up 1, I'm not even getting a point on the graph. And this is telling me that maybe I need to compress this graph a little bit. So I need to either compress it horizontally or I need to like stretch it vertically. And I think stretching it vertically will work. So for example, if I take this graph and I were to stretch it by 2 vertically, this point here would get moved up to this point. So the special point would now be going over 1 and up 2. And that kind of matches what's happening here, going over 1 and up 2. And then I would get another point on the graph up there. When you're just writing the functions, you kind of don't have to worry that this is an open circle, for example. You can just kind of imagine that this function is defined everywhere. And then later on, we'll tell the reader how to restrict the domain. So okay, the long and short was that if I just stretch this function vertically by 2, I can get this kind of shape, where I've moved these 3 special points here. So this special point got moved to this special point, and this special point got moved to that one. Okay, so that's my, so I have the two pieces for it. I guess I need to tell the reader now where to do this h1 business. So what happens here is h1 is only defined. So let's get rid of the parent function now and go back to this. This was our h1, this was our h2, that piece. And so h1 was only defined from -3 to -1, where I actually need to leave out the endpoints. So I only do this when x is in -3 to -1. Okay, so I've kind of solved the individual pieces. Now I just need to assemble them together. And really it's just a matter of rearranging things here and using our piecewise notation. So I'm just going to copy this down. Let's see if we go all the way down here. this was kind of a summary of the information we got. So now I need to tell you what h of x is. Well, h of x will be, I need to use the piecewise notation, so it's kind of open bracket. And first let me tell you where to do things. So I'm going to say if x is in -3, -1, and then there's going to be this other case where x is in 1 to 2. And what do I do? Well, I do h1 of x in this first one, and I do h2 of x in this second case. But okay, I actually have a name for h1 of x, which was 2x plus 2 squared plus 1 on the output. And I had a name for h2 of x, which was just 2. And this is perfectly fine for notation, but if you wanted to convert it to what you usually see, we can replace this x in -3, -1 with -3, let's see, less than x is less than 1. Remembering that these open brackets are like a less than, and the square brackets are like a less than or equal. Okay, so now for the second one, we can kind of do the same thing. If x is in 1, 2, so we're at +1. We don't include +1, so we have x strictly bigger than that. But we can possibly include x equals 2, so we can have x less than or equal to 2. Okay, and they've asked us for a formula as a piecewise function, and there we go. That is the formula. So I'll circle it, box it, highlight it, whatever, to distinguish it from the scratch work that went into the problem, which can be important for the reader, so you may want to include it sometimes. Okay, so that's all for that question. Next up, we have this question about expressing this quadratic function in, vertex form, and then we want to write the vertex as an ordered pair hk. And we're getting this hint here that completing the square may be useful, so let's run with that hint. So let's first just, switch back to the normal pen here. First just rewrite the equation as we see it. 2x squared minus 12x plus 14. So that's my k of x. And I just want to express it in a different form. So I'm not going to apply operations to both sides like I was kind of doing when I was solving for x, that kind of thing. Here I just want to take k of x and just re-express it as something different, this other form of the equation that's a little bit more useful for, say, maximization problems. So I know for completing the square, we want to see a monic polynomial, which means that the coefficient appearing in front of the x squared needs to be a 1. So I need to maybe divide out by this leading coefficient in order to set up that situation. So if I do that, I get something that looks like this, where I just have to be careful to divide every term by 2. Okay, and now there was this kind of strange maneuver we did. So we take minus 6x, and we add on, so I'm just going to add on a funny form of 0. And I guess I should note that plus 7 will still be there kind of at the end, so we'll remember to put that back in. But okay, I'm going to call 0 something else. I'm going to call it plus 6 halves. Let's see, what do we need to do here? 6 halves squared. I want to say that's probably what we want. 6 halves squared. Then I'm just going to subtract it off again. So this whole thing was just 0, so I'm perfectly within my mathematical legal rights to do that. So I just added 0 to something, so I haven't changed its equality, what it's equal to. But I've added a particularly nice form of 0 that allows us to do this thing. So this is going to be x minus 6 halves squared. Oh, and I guess I have to be a little bit careful, because I think I want... I think this is the one we want. So here I've just noticed that these 3 terms here, if I multiply this out, I get them. So I get something that, so I get an x squared, there's that. And I get 2 copies of 6 halves x, which is another word for, 2 copies of negative 6 halves x, which is 6x. and then I multiply this by itself, and I get negative 6 halves times negative 6 halves, which is 6 halves squared. Okay, so now I just need to see what I'm left with. I've accounted for these three terms, and what I'm left with are these two over here. So there's a minus 6 halves squared, and there's a plus 7. Okay, but now I'm almost home free, so maybe I'll just write it up here to save some room. I think what I want to do now is just redistribute this 2 back in, and then just be really careful that I hit everything with the 2. So then I get this whole thing is equal to, so 2 times x minus 6 halves squared and now I want to add on 2 times, well, negative 6 halves squared plus 7. I'm sorry, a lot of stuff kind of happened there, but this is really what I'm doing is thinking about this as its own kind of term being added to that. And so I'm just distributing the multiplication by 2 in, where 2 is hitting the first term and then 2 is hitting the second term. And okay, maybe we're carrying around this 6 halves, so that's a little bit silly. Let's convert that since it's really easy in this case. And then just notice here I've been very careful about where does the negative sign go when I'm squaring things. In this case, the negative sign was on the outside of the thing being squared, and that's really important to keep track of. So let's just simplify this a little bit. I don't want to multiply this out or anything like that. I want to keep the first term as it is. And I want to, so let me just do a little bit of scratch work here. I see 2 times negative 9 plus 7. Okay, so what is negative 9 plus 7? That is a negative 2. And then a 2 times the negative 2, I'm seeing a negative 4. And okay, now I think I'm in vertex form. I see something that looks like some coefficient times x plus or minus something squared, and then I'm just seeing it subtracted, something subtracted off with no x's involved. So this is going to be my h roughly. Well, okay, I should be a little bit careful. So vertex form says I need to have like f of x equals, c, let's see, what is it, x, probably want x minus h plus k. So I just need to be a little bit careful with the signs here. I think this is telling me that h is equal to 3, and k is equal to negative 4. Okay, and let's just double check to see if this works. We want to write now, write the vertex as an ordered pair. So maybe I'll say that the vertex is of this form, hk is equal to 3, negative 4. Okay, so I guess I need to box some stuff and tell my, so what did they actually ask for? They said express the function in vertex form and write the vertex as an ordered pair. So they asked for the function in vertex form. So let me point out where that is for the reader. There's the vertex form. And they asked for this ordered pair, so I'll point out where that is for them too. Okay, so just being a little bit careful about the algebra and following the complete the square technique, and then just remembering kind of what needs to be this sort of funny thing that you have to add in. Kind of uninspired, but you just kind of have to remember sort of what the trick is there. And then just remember you could always sort of reverse engineer by multiplying this thing out to see what you get. Okay, so now we just want to sketch this function using these axes. So we have a vertex, 3, negative 4. So we'll go ahead and label that. So there's 3, negative 4 down here, and I'll make sure to put coordinates on it. Maybe I'll do a little bit of scratch work. So I know somehow in the back of my mind it's something like this, right? It's a parabola. It's facing up because the coefficient here I saw was a positive coefficient instead of a negative one. But I need to be maybe a little bit more precise and label some interesting points. And interesting here is usually something like what are the the intercepts or something. So let me see if we have a little bit of, let's see, yeah, some scratch work over here. We had k of x equal to 2 x minus 3 squared plus 4. Let's go ahead and try to find the x-intercepts. So that's where k of x is equal to 0. So if k of x is equal to 0, then, okay, so we have 0 equal to 2x minus 3 squared plus 4. Okay, so I'll subtract a 4 to the, both sides, and I get negative 4 equals 2x minus 3 squared. I'll go ahead and just divide both sides by 2, and that will give me a negative 2 on this side, and it'll cancel that out. So this is just scratch work. Now I'll take the square root of both sides. So I'll get a, oh wait, yeah, something's gone wrong. Right, we shouldn't be able to take the square root of negative 2, right? Ah, okay. Seems I wrote the equation slightly wrong. This should be a negative 4. Thank goodness. Okay, so let's go back a little bit. This was a negative 4. Really quick, if you ever run into that situation where you're trying to take the square root of a negative here in order to get the like the intercepts, what that's actually telling you is that this quadratic doesn't have an intercept. So this is like a parabola that sits above the x-axis and doesn't intersect it at all. But okay, so let's add a 4 to both sides to get 2x minus 3 squared. Now let's go ahead and divide through by 2 to get this. Now let's go ahead and take the square root of both sides. This is where it would be good in the scratch work to really do these in different steps, because I see alarm bells going off. I'm taking a square root of a square, so I'd want to be really careful about what that does and what I need to look out for. And this turns out to be the case that I need to look out for. So when I do these and cancel them, I get plus or minus this quantity. Or if you want the absolute value of that, and then do this thing where we can remove the absolute value by putting in the plus or minus. And okay, let me just simplify what I have here. I have square root of 2 equals, let's see, plus or minus x. Let's see. Right. Plus or minus needs to go on the other side. Yeah, so this is where it maybe pays to be explicit in your scratch work and like actually write all this stuff out. But okay, if we have this plus or minus root 2 equals x minus 3, let's go ahead and add 3 to both sides. Just being careful to denote that it's not under the square root. And I get something like x equals, let's see, something like square root of 2. Yeah, square root of 2 plus or minus 3. Okay, and then if I just go over here, square root of 2, I mean, who knows, it's like 1.14 or something. So maybe you get something like over here and something over here. And I'm just double checking now, maybe, yeah, I think that should be fine. Yeah, so maybe negative root 2 plus 3, so maybe this is like over here somewhere. So as long as I'm just telling the reader that this is at negative root 2 plus 3, which I think is positive, it's actually probably a little bit bigger than 2 maybe. So you can plug this into your calculator if you'd like. So this is negative root 2 plus 3. And then there was positive root 2 plus 3, which I think is a little bit bigger than 4. So there are my two intercepts. As long as I work those out, then I get something like this. It's not the greatest drawing in the world. But whatever intercepts you come up with, you just want to make sure that you've labeled them on the graph, and you've labeled the vertex as an interesting point, and hopefully in your drawing the graph actually passes through the vertex, and hopefully you get something similar to that. But yeah, it's really important to label at least a few important points here, and then to also indicate with the arrows that this function really does extend everywhere. Okay. Let's see here. So for the next one, we want to find out where the function is increasing, where it's decreasing, where the vertex is. Well, really this is the case for any of these quadratics. You'll have the vertex, and then on one side of the vertex it'll be increasing, on the other side of the vertex it'll be decreasing, at the vertex, it's neither, because we have this horizontal tangent line, right, just happening right here. And so here we can just kind of look at the graph. Fortunately, we've already done this in the previous problem. We see that if we draw these tangent lines on the left-hand side, they're all going to have negative slopes. So if I just draw one there, and they're all negative. And if I'm on the right-hand side, all of these tangent lines now have positive slopes. Oops. Okay, there we go. So what is that saying? Well, it's saying if you're on the left-hand side of this vertex, so where is this vertex? This is occurring at, so there's an x value above it, right at 3. It's saying that if you're anywhere to the left of 3, then you're decreasing, right? Because all of these lines have negative slope. If you're anywhere to the right of 3, then you're increasing, because all of these have positive slope. So I can just tell the reader that, decreasing. The interval is, so it's anything to the left, so it's negative infinity to 3. And we don't include 3 because it was a horizontal tangent line there. And it's increasing on the other side, so just continue on, 3 to infinity. And, well, the vertex we figured out from before. This is 3, negative 4. Just going back up to our graph, if you want, it's that thing there. Or really, we had to write it down as part of the first part of this problem. Okay, so let's look at this next problem. We're given two functions, f and g, and we want to answer some questions about them. F of x is 1 over root x. So this is the function that takes your input, whatever it is, x. The first thing it does is it tries to take the square root of it, and then after doing that, it takes the reciprocal of the result. So that's how this function acts on its inputs. We have this other function g of x, which what does it do? Well, it just takes your input, and then it just subtracts off this capital lambda, which is some unknown real number, but it's just some number, some constant. Okay, so what are the domains and ranges of f? So let's look at, right, for domains, we always want to ask ourselves kind of what are the problematic points? So right, the way I set this up when I was talking about it is that the first thing it tries to do is take the square root of a number. All right, and we know that we have to, if we're thinking about taking the square root of something, we have to throw out all of the negative numbers, right? We don't know how to take the square root of a negative, or the square root doesn't know how to handle negative numbers. And you just have to remember there's this weird thing in 0. The square root does know how to handle 0. The square root of 0 is just 0, so that works out just fine. So the hope is that we hope it's all of r. Just every real number can go in. That would make our lives great if the function just worked on every real number. But we need to throw out some stuff. So let's throw out all negative numbers. Okay, and that's just to kind of get this function off of the ground. I need to evaluate the square root in the bottom first. And that needs to be 0 or some positive numbers. Or in other words, I just need to throw out all of the negatives. Okay, and then I just need to be a little bit careful about when is this thing not defined. When is taking the reciprocal of something not defined? Well, that's going to be a problem if square root of x is equal to 0. Right? Because if I'm thinking about this thing as like 1 over something, then 1 over something where the something is 0 will be a problem, right? So anything in the denominator equaling 0 will be a problem, and this happens exactly when, so if and only if, x is equal to 0. Okay, so that means we have to throw out x equals 0, as it turns out. So we need to throw out all the negative numbers, and we also need to throw out x equals 0. Okay, how do I convert this to an interval? Well, I just think about here's my real line, there's my infinity and negative infinity, there's 0. Let's talk about all the stuff we have to throw out. So all the stuff we have to throw out is over here, all of the negatives, up to, not including 0, so that's just coming from having to throw out all the negative numbers. And then there was a separate thing where we actually had to throw out 0 too, so we have to throw this out. So we're deleting this negative infinity to 0 is deleted. And what are we left with? Well, it's everything over here, do it in a different color, everything in pink. So what's left is 0 to infinity. And I can't include 0, right, because 0 was one of the things I had to throw out. So what's left is 0 to infinity, and that's the thing that, so right, the domain of f is 0 to infinity. It's all of the real numbers, except I've thrown out all of the ones that cause problems, and I'm just keeping whatever I'm left with. Okay, so now I need to know about the range of f. And this one, I mean, you maybe have to reason about it a little bit. You might have to think about, you need to know the range for square root of x. So if you just think about the graph of square root of x, for example, it's something like this. That's, should be a little bit careful. It's y, x. This is maybe h of x is equal to square root of x. So I know that square root of x can take on all possible positive numbers. And then I just have to think about a little bit about the graph of 1 over x. I also know that 1 over x has something like this going on. This is y, this is x, this is, so maybe let's call this h0 of x, and this is h1 of x. This is 1 over x. So I know that 1 over x can attain all positive numbers as well. And so if I'm just like feeding the outputs of one function into another one, so I'm just doing this h0 of x first, I'm taking the square root, and whatever its output is, I'm just feeding it into 1 over x. In other words, I'm composing these functions. I'm seeing that I can actually hit all of the positive real numbers if I want. So I just need to, so maybe you could look at this and kind of try to reason just from the equation. Can I possibly get a negative number out of this? The answer is probably no, right? Because the square root can only ever be positive. Could I get a 0 out of this? No, right? Because, maybe I could plug in a 0 to get a 0 down here, but then I'm trying to divide by 0, and that's a problem. So I can't really get a 0 by taking 1 and dividing it by something else. Can I get a positive number? Can I get any positive number I want? I think so, because if I try to solve y equals 1 over square root of x, and then y is like my favorite positive number, and I want to see is it in the range, I could just kind of solve for this by saying root x is equal to 1 over y, and then x is equal to, 1 over y squared. So I've solved for x in terms of my favorite number y, and this just says if I plug in x equals this number, 1 over y squared, into that equation, then I get my favorite y back. As long as y is positive, I can solve this. And not 0, right? Because here I tried to divide by y. So it's, there's some ways to reason through it, but what ends up happening here is that the range is just all positive numbers. Okay, and then I guess I should be careful. I should box and highlight this for the reader to indicate that this is the answer to the question they were asking. Okay, now they want us to compose these functions. So we're given h is equal to f of f composed g. That's what this notation here is telling us. And we want to write a formula for h. So let's just start with h of x. A formula for h means you should tell me if I give you an x, what is h of x? What is the output of this function in terms of my input? That's what it means to be a formula. Okay, well maybe I'll just write it in this funny way first. We're told that h is just equal to f of g. So h and f composed g, these are just two different names for the same function, except I just happen to know what f and g are. So I can replace h with f and g and then hopefully make some progress by plugging in f and g. Okay, so this is just a weird sort of way of plugging in, or writing this thing, f of g of x. And okay, so what I'll do is I'll work my way inside out. Now if I'm composing functions, I want to start substituting things in. Or I can actually work my way outside in. Let's do it that way. So let's see, what was f? F was the function 1 over square root of x. So let's do that. It's 1 over square root of something. Right? Reminding ourselves that f of x was 1 over square root of x. the way to think about this is that x wasn't really important here. X was just the name. X was the name for the inputs. And the input could be some complicated expression here. So I'm just replacing it with, here, let's maybe do a question mark. And so this just says whatever the input is to f, I just need to put it all underneath a square root sign, and then I need to take the reciprocal. Okay, so what am I feeding into f here? I'm feeding in this g of x. So that's what needs to go in to this. Okay, but then I had another name for g of x, right? G of x was this x minus capital lambda. So I can go ahead and substitute that in now. Okay, and that is my h of x. And that is at least part of the solution. I think they wanted here was just a formula for h of x. And they want to know what is the domain and range of this. Well, so what's happening here, maybe a shortcut way to see it, you could sort of run through the same process of reasoning about, what are the problematic points, what do I need to throw out, that kind of thing. The whole point is that this is just one of these graph transformations, so we don't have to redo the work at all. We're just seeing that this is a shift of the original function f, right? If we just go back here, this was f of x. This is just shifting that graph by lambda units to the right. Right, so that's what it means for when you have the minus sign here. So you need a little bit of math goggles to see that this is actually just the shift, but once you have that, we can use some shortcuts. We know that shifts don't affect the range at all. So the range is just exactly what it was before, 0 to infinity for free. The domain, let's go back up to what we had for f. We saw that the domain was originally 0 to infinity. And what we're doing now is we're shifting this whole graph to the right by lambda units, which means that it shifts its domain by lambda units as well. And so you might have seen in the pre-classes, I had this kind of weird notation for this. I put it in quotes because it doesn't actually mean anything. It's just a mnemonic. But I've taken 0 infinity and I kind of want to add lambda to it. So I just want to shift it over by lambda. And what does this actually mean? This means that you take this whole interval. There's 0, there's infinity. This was my original interval. And you shift it over to this new interval. So here's, maybe let's draw lambda in both of these number lines. There's lambda. And the shift just says, oops, move this whole interval to the right. And you get this one. And if you want, this is just because when you shift that whole graph over to the right by that many units and you look underneath, you're seeing a copy of exactly this real line on the x-axis. Okay, so how do we get an actual answer out of that? Well, if we shift 0 infinity to the right by lambda units, we get lambda to infinity. And that's the precise answer. Okay, and I need to box that as well because that was part of what they were asking for the question, was a formula for h and the domain and the range. And now I'll just go ahead and highlight that for extra measure so that they know this was the intended answer to the question. All right, next up we have three functions, f, g, and h, graph below. And we're told that, say for example, g, which is this function up here, is some shifted, scaled version of f, which is this function here. And we want to just find, so it's written in kind of a weird way. We know that g of x, which is, sorry, this one up here, can be written as, well, something, something, something involving f of x, and then there are a bunch of constants floating around, alpha, gamma, delta, and beta. And the idea is that we can maybe find what these constants are. Okay, and what are some ways to think about this? Well, let's see. So I'd like to pick one point to sort of follow it through. So we know that we're going to need to shift it, so let's see where this middle point needs to go. So I need to send that to this middle point to get g. Let me do it in a different color here. So what shifts do I need to accomplish that? I need to go to the left by 3 units, it looks like. I need to go up by 3 units. And the question is, do I have to do any stretching or any kind of compressing or anything like that. Let's just see what happens when I shift, let's say, this other special point following these instructions, shifting it over by 3 and up by 3. So I get 1, 2, 3, and then 1, 2, 3, and I see it lands exactly on that point. So I think that's fine. I can do the same thing with this point. I do 1, 2, 3, and then 1, 2, 1, 2, 3, and I actually land at this point. So I know that at least these endpoints are getting matched up as well. So that's a good sign. So these are all, if I just do the shifts by themselves, I'm mapping these original 3 pink points to these 3 up here. How can I tell if I need to, so that's what that's telling me is there's no horizontal scaling that I need to do. How do I know if I need to do vertical scaling? Let's maybe look at this point here. What happens if I shift it over by the prescribed amount? I actually land here, so that's good. And if I take this one here, let's do the same game. 2, 3, 1, 2, 3. I land there. So this is telling me that if I shift this point, I end up here. If I shift this point, I end up here. And so it looks like I don't have to do any vertical scaling either. So I just need to do horizontal by 3, a horizontal shift by 3, a vertical shift by 3, and no scaling. So now I just need to interpret which of these parameters do what. So here's alpha, beta, gamma, and delta. So I think this one is telling me about horizontal shifting. All right, so plus delta. And I want to shift it to the left. And if I just plug in 3 for delta, this will become like a plus 3. And plus 3 indeed shifts me to the left, remembering that the horizontal things are a little counterintuitive. You might think it's a minus 3 to the left, but it's always a plus 3 when it's horizontal. And I know that the beta, this is the thing that's, we're adding on to the outputs of the function, so that's shifting us up or down. And so if I just put in a 3, this becomes something like a plus 3, so that's giving me the upwards shift. Now I just need to be a little bit careful about what is this alpha and what is this gamma. And so what happens here is that these just need to be 1, because what happens here is after you plug all this stuff in, you get f of x plus 3 plus 3. And that's exactly doing a horizontal shift to the left by 3 and a vertical shift up by 3. And it's tempting here to maybe think maybe just alpha is 0 and maybe gamma is 0. That's a little bit of a problem, right? Because if alpha is 0, for example, then this whole thing gets zeroed out. And so you just end up with just like a plus 3 left over. You get g of x equals plus 3. And so that's just a constant function. So you don't want to do that. It's like you've kind of squished the graph down by scaling it with the 0 out in front. And if you plug in gamma equals 0, kind of the same thing happens. You sort of zero out that x, and it kind of crushes the graph a little bit. So you don't want to do that. These are the 4 you want. And there we have it. Maybe I'll just go ahead and highlight these. So we have that. Okay, and the next question down here is the function h can be written in terms of f. Well, it's the same thing except for just the other function now, the one on the right. So let's just play the same game. We remove all of this to declutter it. First thing I'm going to do is trace out where does my special point go. So I want to follow that one right in the center. I've just picked for, no particular reason except for that it's sort of an easy point to see on all 3 graphs. We can see it lands there on that graph, and we can see it lands there on that. And so I want to see what do I need to do to get that center point lined up. So I need to go over by 1, 2, 3. So that's a shift to the right by plus 3. And it looks like I need to go up by 3, plus 3. Okay, so I'll definitely need those shifts. Let's follow these 2 endpoints here. If I just do the prescribed shifts, and okay, that point gets mapped to that point. So it seems like we're all good here. So this is shift up by 3. And if I do that to this point, I end up there. And the same kind of thing happens with this point. If I just go over by, 1, 2, 3, then go up by 1, 2, 3, that lands there. So these points are getting matched up pretty nicely. And now just to check, so it's saying that, so the first point was telling me about what kind of shifting I need to do. And then I've checked some points that would tell me about horizontal scaling. If this point ended up somewhere radically different than this point, if it ended up kind of over here or something like that, that would be telling me that I need to maybe do some horizontal stretching or compressing or something. But since these already end up at the right points, these two, like this one ends up here, this one ends up here, that's telling me I don't need horizontal scaling. So it's really just the vertical scaling I need to check now. So let's just follow the prescribed shift. If we do 3, so it's 1, 2, 3. Oops, 1, 2, 3. There we go. And then 1, 2, 3. Okay, so that's not quite right. If we just follow the prescribed shifts, it doesn't send this maximum point to the right maximum point there. So this is telling me that I need to do some kind of vertical scaling. How am I going to figure out what that is? Well, I can see here that sort of maybe how do I get from this special point to this special point? I kind of go over by 1 and up by 1. And what's happening in this case? Here I need to kind of go over by 1, and now I need to go up by 2. So I need to kind of double the vertical distance that I'm traveling. So this is telling me that I need a vertical scale by 2. Okay. So let's just sum up what we have. We have this horizontal shift by 3. We had this vertical shift by 3. And we have this vertical scale by 2. So now I just need to figure out what goes where. So there's alpha, beta, gamma, and delta. Okay, so delta was the horizontal shift. This was something that we needed to, let's see, so we needed to shift it to the right by 3, which means that we actually need this to be a -3 now. Beta was the thing telling us about the vertical shift, so that's still a +3. Gamma is the thing operating on the x's, so it's operating on the inputs. The inputs are, these have to do with horizontal things. And we saw that we're not changing anything horizontally, so that'll be a 1. And then the alpha thing, so we needed to stretch vertically by a factor of 2, so this will be a 2. And you might be tempted here to say, is it not 1/2 or something? But just remember that it's really only the input modifications, the horizontal modifications, that have this counterintuitive behavior. When you're doing vertical things, stretching it by 2 is literally multiplication by 2. If you're doing it horizontally, then stretching it out by 2 would be multiplication by 1/2. But okay, so we have a solution. Go ahead and box it. And maybe highlight it. In this case, I don't think you really had to explain too much on this question in the exam. You can just sort of, if you get really good at these and you practice a lot, you can kind of eyeball what the transformation needs to be. And that's totally fine in this case. Okay, so now we get to the last two problems, which were on the more complicated side, and this was sort of intentional. Sorry, let me pull up the... I have to just make sure I'm very careful about how I work these out. Oh no, my mouse has died, apparently. Okay, so I will edit this part out. Okay. Okay, so next up we'll go ahead and look at problem 6. In this one we're given a slightly more difficult word problem. And hopefully, okay, if you've worked the exam, you've kind of read it over and you have an idea of the situation. I want to talk a little bit about how do we extract the actual mathematical thing this is asking, how do we get equations out of it. So the idea here is we have x is kind of our independent variable, so we're trying to produce x items, and we're trying to figure out the cost. The cost is going to be some kind of function. These are the outputs we're probably concerned about, is what is the output cost as a function of the input number of items. And we're told that it's always a linear function. So a linear function should be screaming out, we have these three things, right? To talk about linear functions, we have point slope, point point, slope-intercept form. So in just reading this question and seeing linear function, I'm thinking to myself, I'm probably going to use one of these tools to build a linear function. Okay, so we have two vendors submitting bids to produce this widget, and we see that company A will provide 1,000 items at a cost of $7,500, and the cost will increase by 90 cents per each additional item. And then for company B, we see that they provide 900 items at a cost of $7,600, and they'll provide 1,200 items at a cost of $7,780. So I think what's difficult here is to realize that this linear function thing is really important. So they're not just saying, in this case, that they'll only do 1,000 items or something. In this case, you can see that they're saying they're willing to do 1,001 items for $7,500 and 90 cents. And you can imagine doing 1,002 items at $7,500 plus 90 cents twice. So something like that. So what they're actually giving us is they're giving us, so for company A, for example, let's look at this one first. They're giving us a point. That's right, we have to kind of have in the back of our minds, what are we going to be plotting? The inputs are going to be x's, the outputs are going to be maybe c's. So c is going to be a function of x. And we're going to have two functions of some kind. There's going to be an a of x. So this is whatever cost company A decides to, whatever the cost function is for company A. And we'll have some other function b of x, which is also a line. And at some point these lines will intersect. And maybe if you want to, let me do a different color here. If you wanted to order this many items, you could just go up to the functions and ask which one has the lower cost at that point. Sorry, didn't draw that super accurately. But the point is that they're willing to sell you any amount of items, but the cost there's some kind of formula to compute that cost. So what's the formula? That's the name of the game here. We're told that it's a linear function. And so here we have to think about, we're given 1,000 items, which is, we have a point. Maybe let's call it P0. And it's given in coordinates by, what are the x's? The x's were items, so there's 1,000 items. And then the cost is $7,500. So there's a point. And what is this other piece of information that they're telling us here? It's 90 cents per each additional item. And so if you think about it, they're telling you something about this like marginal rate of change. We talked a tiny bit about this, but they're saying something about the slope here. They're saying that the slope is 0. Well, let me write it this way, slope. So there's a point. And they're telling you about this rate of change where it's 0.90 dollars for one item. Remember that these were items, these were dollars. We can label that on the graph if we want. These were dollars, these are items. Okay, so they're telling you something about the slope. It's $0.9 for one item. Maybe it's just easiest here to rewrite that as 0.9 out of 1, and we'll worry about units a little bit later. And maybe just to rewrite this, to keep things a little bit easier, I'll just write that as 9/10. So it's a slope of 9/10. But okay, now we know we have an algorithm for coming up with sort of an equation of a line given a point and a slope. And so the equation goes something like this. So maybe I want to call this m naught is 9/10. This is our slope. So maybe let's call this x naught and c naught. And the point slope formula went something like this. It was c, so the output variables, minus c naught equals m naught times x minus x naught. So it's important that the input variables get grouped together and the output variables are as well. Okay, but now I can just start plugging stuff in. C, and now I need to see what did I call c naught? It was that thing there, minus 7,500 is equal to m naught. I had a name for that, 9/10. And there's an x, and I had a name for x naught, which was, by this labeling here, just 1,000, minus 1,000. Okay, and then there's the step we talked about, so maybe I'll just go ahead and add 7,500 to both sides, and then I'll think of c now as a function of x, and so it's 9/10 x minus 1,000 plus 7,500, and I'll leave it to you to sort of sort out what this simplifies to, but you end up getting 9/10 x plus 6,600, as long as you're careful about the algebra there. And now we have an equation, c of x. Let's maybe go ahead and call this c sub a of x to denote that this is the function associated with company A. So over here, I guess we're calling this c sub a of x now. So the cost of company A as a function of x. Let's call this other one c sub v of x or something now, because the outputs are these c's, these costs. Okay, so that is one of the functions. Let me go ahead and shrink that, move it out of the way a little bit. We'll need to come back later and simplify, figure out what the question was actually asking for, but let's look at company B now. Okay, so company B now says they'll give us 900 items at a cost of 7,600, and they'll give us 1,200 items at a cost of 7,780. And if you think about it, they're totally willing to sell us 1,000 items. It's just at some cost in between these two, right? So we just need to figure out what the function is that lets us evaluate that. If you think about it, we're given 2 points. There's an input value and an output value, and there's another input value and an output value. So we're given points. Let's say P naught is equal to, I'll just call it X naught and C naught. We're given P1 is equal to X1 and C1. And let's see, X naught and C naught are maybe this first price point. It's 900 items at 7,600. The inputs were the items, so that's 900. The outputs were the costs, 7,600. And that's a point. Now what's the other point? The other point was 1,200 items at a cost of 7,800. The items were the inputs, it's 1,200. The costs were the outputs, 7,800. And so we have 2 points. And I should be thinking point formula for this guy. But really, we remember that there was an algorithm to do this. And step 1 was compute the slope. So we need a slope. And it was the difference in the outputs. I guess we can take them C1 minus C naught over X1 minus X naught. So the difference in outputs over the difference in inputs. Okay, but now I've told the reader what C naught is. I just have a name for it, 7,600. And I've told the reader what C1 is. It's 7,800. So there's 7,800 minus 7,600 I'm seeing in the numerator. And then I've also told the reader what X naught and X1 are. So X1 was 1,200 and X naught was 900. If we simplify this, I think we get 200 in the numerator and 300 in the denominator. Hopefully. Oh, whoops. I see something went slightly wrong here. The output cost was 77.80. So let me just correct that really quickly. This output cost was 77.80, and that was our C1. So this should be 77.80. And so this ends up being 180 here. And okay, so this is 18 out of 30. This is, let's maybe divide through by 3. 6 out of 10. And divide by 2, so it's 3/5. So that's our slope. And now we can do point slope with either of our points. So in this case, we have C minus, let's do C naught, equals M x minus x naught. And just remember that I have names for C naught, there it is, and also names for x naught, there it is. So I can go ahead and write that C minus 7,600, just plugging things into my general formula now, is equal to a 3/5 was the slope I got from above, and x minus x naught, which was x minus 900. And so maybe I'll just rewrite this as c sub b of x. Once you subtract 7600 over, sort of simplify everything out, you end up with something like 3/5 x plus 70/60. Okay, so we're kind of in the weeds there. Let's go back and figure out what the function was originally asking us. Determine the functions that provide the cost given the number of items. Well, okay, I think that's kind of what we ended up with at the end. There was the function, which we knew to be linear, and then we solved using kind of point and slope from there. And that was the function for A. And for B, we saw that we had 2 points, so we got a function, again, knowing it was linear, we got this function out. Okay, so now the question for part B is, now we want to order 1,400 items, and we want to know who has the better deal. So this is a specific number of inputs, x equals 1,400, and since we know the cost depends on the number of inputs, we can just evaluate the function at this number. So we just want to really evaluate CA at 1,400 and get something, and evaluate CB at 1,400 and get something. And all that really amounts to here is, so there's my 1,400. There we go. So really it's just amounting to plugging 1,400 in there and plugging 1,400 in there and just seeing what numbers you get out of that. And I'll leave it to you to go ahead and run through the calculations and see what you get. But this ends up being, I mean, at this point, if you want, you can even plug it into your calculator if you'd like. This one ends up being 7860, and this one ends up being 7440. And let's just remember that this was like a number of items, some fixed number of items that we want to buy, and this was a cost. These were the outputs in dollars. And which company offers the better deal? The better deal is definitely the lower cost, right, for the same amount of items. Right, I guess assuming, right, where does it say? It's, yeah, assuming the quality is the same, right? So just which one has the lower cost? Definitely this one here. But maybe I need to tell the reader something about, like, what's the actual answer? The better deal. Company B. Why? Lower cost. And right, so they asked in the question for some full justification of the answer. And that's all you really need to say. It's just that I've plugged this number into this formula. I'm just interpreting the outputs. I'm interpreting that the outputs were the cost of that each company would charge for this number of items. And the better deal is definitely the lower cost in this case. Okay, so this last question is meant to be pretty difficult, but also shows up in the notes a little bit and is similar to some stuff that shows up on some of the worksheets. So in this question, we're asked to build a rectangular region in quadrant 1 of the Cartesian plane, and we have some instructions for kind of how this should be built. And this is probably going to be a maximization problem, like we're building some small like fence or something in this region, and we want it to enclose the maximum number of area, area at the end. So I just want to go ahead and follow these instructions first, because this is asking us in this first part of the question to go ahead and just sketch a picture of the situation, including the x and y intercepts. And we'll sketch some theoretical region R according to these instructions. So let's just go through the instructions. We're going to build a rectangular region. One side is going to be along the line x equals 0. One side is going to be along the line y equals 0. And then it's going to have a top right corner on this line given by some equation. Okay, so where do I even start? Well, I'm just going to hone in on this. I'm in quadrant 1 of the Cartesian plane, so I know at least how to start this drawing by just drawing a copy of the Cartesian plane, which is just a fancy name for the xy axes that we're used to. So there's the y-axis. There's the x-axis. We're in quadrant 1, so Q1, right, is this top right corner. We know that one side is going to be along this axis. Let's see, the line x equals 0, so that's going to be where one side lies. We know that the other side is going to lie along the line. Sorry, I just read that wrong. If we one side is along the line x equals 0, which is actually this, and so that's the x equals 0. One side is along y equals 0, so that's going to be this line. And then the top right corner will now be, find a different color for this, will be on this line, L given by this equation. Okay, so we don't know what this lambda is, but we can kind of sketch a cartoon of this situation by just looking and seeing, okay, this is some line with a negative slope. So I don't really have to be super, super precise when I go to graph it. I just know it's something like this. And I need to be maybe a little bit careful. So I need to indicate that it goes off forever on both sides. Maybe now I'll also come in and do some labeling to tell you that this is the line given by the equation negative 2x. Y equals negative 2x plus this capital lambda. Okay, and I know what's happening here is the bottom side of whatever so whatever region I'm building, or rather the corner of it needs to be on this line. So there's a top right corner, for example. And the sides are going to be along these axes. So I'm getting some kind of box like this. Let me make this slightly bigger so it's more visible. So here's our theoretical box. The top right corner is on the line. The left-hand side is along y equals 0. So right there's the top right corner. Left-hand side is along y equals 0. X equals 0. The bottom is along the line y equals 0. And then we have some region R inside. And we'll have a point up here on the corner. Who knows what it is, but I'll just call it xy. These will be variables we need to figure out, because if I change xy, I'm getting boxes of different dimensions. And maybe just to be really, really precise here, maybe I see some interesting points that I want to label, the intercepts. So let me just do some scratch work over here. What is this intercept here? I get this by setting, so I need to take y equals negative 2x plus lambda and set x equal to 0. Then I get y is equal to, well, negative 2 times 0, which is 0. And then I get a lambda there. So I know that this intercept is occurring at 0 in the x direction and lambda in the y direction. And let's look at this intercept too. Here, let me do some scratch work over here. So I want to set now y equal to 0 in y equals negative 2x plus lambda. So then I get something like 0 equals negative 2x plus lambda. And, okay, subtract lambda over and divide through by negative 2. I get x equals lambda halves. So here I have something that looks like lambda halves and 0. Again, the lambda is just coming along for the ride. It's some number. It's just unknown to us, but it's not an actual variable. So you can just pretend it's 3 for all it really matters. But for example, you wouldn't want to accidentally, if you pretended it was 4, that would be bad here, because then you would be tempted to divide 4 by 2 and simplify that to a 2. So we kind of lose track of some stuff. Okay, and really this is all we really need for the sketch of the situation. We've just kind of followed the geometry instructions they've given us in the first part. Okay, so now we need to know something about the enclosed area of the region R, and it should somehow depend on x and y. And so this is this question here. The area A of A should depend on x and y. So this region R, it depends on x and y, and it could also involve this lambda that's floating around. In fact, all of this problem throughout the entire thing, the lambda could show up kind of anywhere. So let's just go back to our picture. What is the area of this region? Area, well, it depends on x and y, right? Because if I change x and y a little bit, if I start moving x, y down the line, say down here maybe, then I'm getting kind of a longer rectangular box of some kind. And that'll probably have a different area. Similarly, if I move this xy up like that, then I'll get some sort of tall box like that, and that's going to most likely be a different area as well. But okay, if I just have this fixed x and y, what is the area of this region? Well, I just look at it's really, okay, the width times the height. But what is the width and the height here? We see it actually depends on x and y. So I guess this is the width and this is the height. And if you just kind of stare at it for a second, you realize that the width is actually just the x value, right? Because if I just trace this point down here, then I get a copy of x there. And by a similar sort of reasoning, you see that y is the value that's happening on the axis there. And this width is just the distance between, let's say, this point here and this point here, which is literally just the x value. And the height is the distance between this point here and this point here at 0, and that's literally just the y value. Sorry, I'm kind of losing my voice a little bit here. So really the area is just going to be x times y, so the width times the height. Okay, so we've done the work for this, so let's just go put it in the right place. So let's see, paste it there, make it slightly bigger, and I will maybe put some kind of box around it or something. In case there was other scratch work here, I'd want to indicate to my reader that this is the actual thing they were looking for. They were asking about a of x, y. Okay, next up we want to write this constraint function that relates x and y. So this constraint word is a little bit weird. We maybe haven't seen it used in this specific way, but all I want to do is somehow, it's exactly the same kind of things you've seen in the worksheets. I want to somehow relate x and y in some way, because this thing is a function of 2 variables, and I don't know how to handle that. I want to bring it down to a function of 1 variable so I can do my pre-calculus stuff on it. And so I need some kind of function that relates x and y so I can like solve for x in terms of y and then plug it in at the end of the day. But the thing to key in on here is there any relation between x and y? And so let's go up here to the picture. So here's my point, x, y. And we can see that because it's on this line L, they actually have to be related in a very specific way. That if I have this point x, y, x is whatever, but then the y is actually exactly this other point. So I can't just have any y. I can't have some point x, y way out here, because this isn't really following the rules of the problem. They've kind of specified that this top right corner really needs to be on this specific line. So there are plenty of choices of x's and y's that aren't valid. And all the valid choices have this very specific relation where y is related to x in this way because it's on this line. So it takes a little bit of thinking about, but really this is the exact, copy that, that's the exact relation we want there. Just something that relates y and x or constrains them in some way. So I'll just put that in here. So that's all we really need for that part. I'll put a box around it and highlight it just so the reader knows that's, in case I had other scratch work or something, that's the kind of thing that was they were looking for. All right, and now we're sort of at the penultimate step. Kind of the thing we want to do here is find the maximum area that can be enclosed by this region. And so what's going to happen is that we have a of x and y, and we have an equation for that, x times y. How do we find the maximum? Gosh, I don't know. Equations with 2 variables are hard to deal with. Let's try to make it easier by trying to write this as an equation in 1 variable, x. So it can involve x, and it can't involve y. So how am I going to get rid of y? Well, I just have another name for y. And luckily that name only involves x. And, well, okay, maybe this unknown lambda, but that's fine. So I just have this other name for, maybe do it in a different color here. So there's y, and that's a negative 2x plus this lambda. Again, just another name for y. And, okay, maybe I can multiply this out a little bit. It's negative 2x squared plus lambda x. Okay, so I have some kind of quadratic, and the question is how am I going to maximize this? And, well, in the back of my mind, I kind of know whatever I have. Let's see, so this is a quadratic with a coefficient in front which has a negative sign on it. So I think I'm seeing something like this. If I'm thinking about outputs and inputs, so the inputs are x's, and these outputs are areas in terms of x. Maybe I'll just write A for area. And so I'm kind of thinking that vertex is really what I want, right? Because I know that that's it's going to be some point x and A of x. And since it's highest up, right, in terms of the A's, that's telling me about maximum areas. So the usual kind of procedure is going to work here. How do we find the vertex? Well, yeah, really the only technique we have here is to put it in vertex form. So I'll just kind of run through the usual sort of business here. I'll factor out this -2, because I can only do this trick of completing the square on these monic polynomials where there's a 1 in front of the first coefficient. I need to be a little bit careful, so I need to subtract off a lambda over 2x. Right, so I'm just factoring out a -2. So I just check that when I multiply this back in, I get a -2x squared. Okay, that's what's showing up there. When I multiply this back in, I'm getting a -2 times a negative lambda over 2. And that is indeed a positive lambda, so I'm getting this coefficient back. Okay, so I pulled out a -2 correctly. Now I do this slightly weird step where I add in this funky form of 0. And what do I need to do? I need to look at this term. I need to add in plus 1/2 of it squared. So lambda over 2 squared. And I need to subtract that off as well. All right, to keep everything perfectly mathematically legal, if I want this to be an equality, so if I want this to be an equality, then I need to, I can only add 0 to it if I don't want to change the equality. And let's see, so the point of this maneuver is that we can do this here. So I get an x minus, so I'm just leaving this in this kind of weird form just to indicate where everything goes. So this is accounting for these first 3 terms here. If you just square this thing back out, sorry, this square shouldn't be here. But if you square this thing back out, what do you get? You get an x squared in the first term. You get 2 copies of this multiplied by x. So 2 halves of a thing make a whole of a thing, so you get 1 of these. And then you get this thing multiplied by itself. Well, that's indeed this thing squared coming in with a positive sign. Okay, so I've accounted for those first 3 terms. What am I left with? This lambda over 2 squared coming in with a negative sign. So just this stuff here. Okay, and just about done really. I just need to distribute things back in. So I get a -2 x minus, okay, maybe now I'll be a little bit less silly. Let's go ahead and pull that 2 into the denominator. So lambda over 2 is just lambda over 4. And I need to square that entire thing. So maybe I'll just do this in a different color since we have so many parentheses floating around. And I have, well, plus 2 times lambda over 4 squared by taking this thing, multiplying it in, distributing it in to multiply that. And this is my vertex form, right? So I have a vertex at, what are the coordinates? Well, it's an h and a k. And so maybe here is my h, here is my, this whole thing here is my k. And so the vertex I get is something like lambda over 4 coming from my h, and 2 times lambda over 4 squared coming in as my k, right, just this entire term here. And okay, so now I just need to interpret what I've actually done. So let me just copy this down here. Now that we've done this huge computation, we have this vertex. Just remember that we were plotting this on an x versus a, and the a's were just areas. and the x's were actually like some values of x. I guess these were widths that we could change. And so this means that if we're interpreting this plot to be something like this, and we have this vertex up here at whatever it is, lambda over 4, 2 lambda over 4 squared, then this second coordinate, this k, is telling us about areas. So that's the one we read off. So that's telling us that the max area is 2 times lambda over 4 squared. And that's the thing they were originally asking for, so I'll go ahead and box that up, highlight it to let them know. And I guess we should maybe be a little bit careful. Maybe there's units or something of square feet. I think if that's, I don't know if they gave that to us in the problem. Let me double check. Yeah, maybe not. So they didn't specify the units, but if there were, then you would definitely want to include them. And it seems a little weird because this lambda is still showing up in the output, but that just means that we've solved a general maximization problem. So if we go all the way back up, if they, so lambda was kind of this unknown line. So you could imagine if somebody came in later and said, oh, I want to put it on a different line, maybe instead of 2x plus lambda equals 3, they want to move it to 2x equals negative 2x plus lambda, where lambda is 4 or something like that. And what that would do is it would just change, sorry, let me do a different color here. Like this and this. It would just move this whole line up to something like this, and then you would get some kind of different situation with the box. Now maybe it goes out to here or something like that. Erase some of this stuff to declutter it. So yeah, you can imagine if they change their mind and they now want a box out on this line for whatever reason, then now you don't have to redo the problem. So maybe this is like y equals negative 2x plus lambda prime, where lambda prime is like they've chosen some different number for some reason. But the point is now we don't have to redo this whole maximization problem. We did it in terms of this unknown lambda, so we don't have to run through all of these steps again. We can just jump straight to the end and say, look, here's the maximum area in terms of that lambda you gave us. So if you decide to change your line, okay, just plug your new lambda into this equation, and this is going to tell you what the maximum area is based on your choice now. Okay, so that's the end of this exam. It's a little bit long to go over, right? I guess this ended up at just about 2 hours, because I probably spent about twice as long for each question, discussing some of the problem, some of the way you might think about the problem, or what might motivate it, where it's coming from, how to approach it if you didn't know what to write down. If you do have questions about it, go ahead and email me, but hopefully this is useful to you guys. So thank you, and I will see you all in class.